the functional programming toolkit. And what this talk is about is it's kind of like design patterns for functional programming. Everyone's familiar with object-oriented design patterns, I think. In functional programming, it's not really design patterns. It's really a set of tools almost that you can use to build programs. And once you understand how these tools work, it makes it a lot easier to understand any functional programming code. And if the toolkit is the common across all different functional programming, so it's nothing to do with F# or Haskell or anything. It's the same. You can use these same tools in any programming language. So I'm Scott Wlaschin. If you need to contact me on Twitter, that's my handle, and I have this F# site. But this is, like I say, this is not really to do with F#. This is really any kind of language. So what I'm going to try and do is answer, why do functional programmers use so many strange words? There's all these words like functor and catamorphism and applicative and currying and monoid and monad. They're very scary sounding words. And I understand why they're so scary, you know, because you've never seen them before and they just sound scary. But I actually think it's not that they're scary; it's that they're unfamiliar. If you understood them a bit, they wouldn't be quite so scary. So especially if you can call them different words, if you called things mappables or collapsibles or aggregatables or chainables, if we used words which weren't so mathematical, it would be a lot less scary. And I think that's one of the problems with functional programming in general. But anyway, the words are what they are, but I will try and explain them and demystify them in this talk. So even if you don't understand what they all do, because that takes a bit of practice, at least they won't be so scary. At least you can look at them and you can say, well, okay, I understand vaguely what they do. I need to learn more about it, but I'm not going to be scared by them, you know? So I don't think functional programming should be so scary for people. Now, I'll tell you what should be scary for people is object-oriented programming. So object-oriented programming has all these scary words in it, you know, polymorphism and covariance and solid. And solid stands for 5 other different abbreviations, and there's DEI and ABC, MVC, IOC. There's a lot of jargon in object-oriented programming too. But you don't think of it as scary, probably because you're used to it, because you've been learning it for a long time. But I mean, the functional programming jargon is not any more scary than the object-oriented jargon. I guess that's just the point I'm trying to make here. So if you can understand all the object-oriented jargon and not be scared, you can totally understand the functional programming jargon and not be scared either. So, so don't you know, like I say, OO is pretty scary. Now, the other thing about these words is they sound like they're very theoretical words. They're very academic words that the only intellectual or academic people will use. It's actually not true. These are very useful tools that any programmer can use for any kind of job. And that's what I'm going to try and demonstrate in this talk. These are useful tools, and why are they useful? That's what I want to show you. So I like to think of these things as a functional toolbox. So here is a toolbox with some tools in it. And just like a craftsman has a bunch of tools they use, functional programmers have a bunch of tools they use. And there's about 11 of them. There's one called map, there's one called return and combine and bind and apply. Like I say, there's only about 11 things you need to understand. And again, when you're new, these won't make any sense, but once you get the hang of it, these are tools that you'll reach for. Every time you have a certain kind of problem, you can say, I need this kind of tool to solve my problem. And that's what these are. That's why I prefer to use tools rather than patterns. So it's a problem-solving thing. It's not just an academic theoretical thing. So the first problem you typically have to do is, how do you do composition? Functional programmers love to do composition, and most of the tools are about composition. How do you combine things? How do you aggregate things? How do you loop over things? How do you iterate over things? How do you work with effects? And I'm going to explain what I mean by effects very shortly. But effects are basically things that change. Your program changes something like, writes to a database, or it changes a variable, or it's an optional piece of data. Those kind of things. So you have to mix these things together. That's can be complicated. You want to chain them together. That can be complicated. You can work with them parallel. That can be complicated. So all the tools are mostly to solve these kinds of problems. So the words that I'm going to use are simple words. I'm going to use, for combining things, I'm going to use compose. Fold is the word used for iterating over a loop, and I'm not going to have time to cover that today. Combining and reducing, I'm going to talk about that today. And then working with effects, map and return, and bind, which is also known as flat map, and apply, and last one I don't have time to do. But basically I'm going to talk about like 5 of these things today, and I just want to show you that they're not actually so scary. And I'm using words that you might find in a library like map or combine. Now the jargony words, there's more complicated versions of these. Of course, this is the functional programming jargon is to use a word like a monoid when you combine things. Rather than just combining things, you call it a monoid. And when you're mixing things together, you might call it a functor or a monad or an applicative. So that's the jargon. But I'm going to try and avoid using the jargon too much, and I'm going to try and focus on the core concepts of why these things are important. So just like any kind of talk, this is a short talk. I can't really explain everything in a few minutes. It's like one of those bus tours where you see all the big famous tourist sites, but you don't really get a chance to stop and look at them in detail. So it's just a quick tour. So that's what this tour is. This talk is just a quick tour of all the different things you can do. But hopefully it will demystify it a bit, and then you can go back later and try and understand them more. So don't worry if you don't understand everything. That's, I guess, what I'm trying to say. I'm going to go through quite a lot of stuff quite quickly, and I just want to show you that they're not so scary. So before I get started on the toolkit, I just need to go over the core principles of functional programming for people who are not familiar with that. So the core principles of functional programming, statically typed functional programming like Haskell or F# or OCaml or Reason or Elm, it's that functions are things, and I'm going to use a railway track analogy a lot, and that you build bigger things using composition. So you don't use inheritance, you use composition. And if you know how to use Lego, you know how to do composition. So functions as things, what does that mean? So a function is something that turns inputs into outputs. There's a little piece of railway track, and on the railway track, there's a kind of tunnel, and it transforms. When the thing goes into the tunnel, it comes out as something different. So like, say, an apple goes into the tunnel and it comes out as a banana. So this is a function that turns apples into bananas. And we would write that apple, arrow, banana. That's typically how we write the definition of the type of a function. Okay, so that's all the function is. That's pretty straightforward. The most important thing to remember, though, is that functions are standalone things. They are not attached to a class. And that means that these, just like you have integers and strings as things that you can pass around, functions are things that you can pass around. You can pass a function as an input to another function. You can have an output of a function be another function. So they're just things like integers and strings. So because it's a standalone thing, that's another word for reusable thing. They're not connected to a class, so they don't have to be. You don't have a special refactoring tool if you want to move them from one class to another. They're always completely standalone. So there's no they're not tangled up with anything. So here is an example of a big function, and it has a regular input. At the output is another function. So this is a function that spits out new functions. Here is a function, and the input is a function, and the output is something normal. So this is using a function as an input. And here's a function with a normal input and a normal output, but there's an extra parameter, which is another function which controls how the main function works. So this is what you might call the strategy pattern in object-oriented programming. There's some extra thing you pass in that controls how the main thing works. And in functional programming, everything is a function. So we pass in functions that control how other functions work. And this is the basic idea between functional programming. Everything can be built from this simple foundation. It can get very, very complicated. You can have a function that has a function as an input and a function as an output, and that other function generates new functions. You can get very complicated, but the core principle is very straightforward. Now, one thing I'm going to focus on a lot is when you have a function which has a function as an input and a function as an output. And these I will call function transformers. They turn one kind of function into another kind of function. And most of the functions in the functional toolbox are these kinds of things. They turn one kind of function into another kind of function. So I'll go into quite a lot of detail about that. Now, the other core principle that I want to focus on is composition, like Lego. So if you think about Lego, there's actually a sort of philosophy behind Lego, that in Lego, all the pieces are designed to be connected. And if you connect any two pieces, you get another kind of Lego piece that you can use to add other pieces to. And all the pieces are reusable, right? You can't, a piece can be used anywhere. You don't have to only use it in one place. So here is all the pieces being designed to be connected. They all have the little bumps on them. Here is example of connecting Lego pieces to make a bigger piece. And as after the first step, you have another piece of Lego, and then you have another piece of Lego, and you can keep adding and adding and adding new pieces to the existing pieces. You don't need any special adapters. You don't need to do anything weird. All pieces can be added to, right? And so you can keep adding and adding and adding. And then finally, of course, you can make something out of Lego, and then you can break it apart and make something else out of the same pieces. So and that only works because the pieces are self-contained. There's no strings attached to bits of Lego, right? That each piece of Lego is an independent piece. So this is the kind of philosophy we're going to transfer to functional programming as well. Now, making big things from small things, you can get some amazing things. So you don't have to sort of stop at some point. You can actually take a bunch of small pieces of Lego and make a really, really big piece of Lego like this. And it's the same thing when you make a functional program. You can start with lots of little small functions and make a really big function, which is the entire program. So that's what I like to call the power of composition. Now, functional programming has a very similar philosophy. You design functions that do one thing well, small functions that do one thing well, and each function can be reused. And then you design the functions to work together, because you expect that each piece might be used in different contexts. So you make sure that the output and the inputs are, you design them so they're useful to other people. They're not just useful to one thing. And in statically typed functional program, we have types. So the input and the output is a static type. And we can use that to make sure that we can't mix them up. So if the output is an integer and the input is a string, that's an error. But if the output is an integer and the input for the next function is also an integer, then that's correct. And the compiler will tell you whether it works or whether it doesn't work. So that's what types are used for. And basically, designing these things that do one thing well, that is what the functional toolkit. These are special functions that do one thing well, and they can be reused as a kind of library. So here's function composition. It's pretty straightforward. It sounds kind of mysterious, but here's a function that turns apples into bananas. And here's another function that turns bananas into cherries, and you want to combine them. Well, it's pretty obvious how you combine them. You just connect the output to the input, and you have a new function. So that's before and that's afterwards. And that's how you build a bigger function from a smaller function. And what's cool is this new function, you cannot tell that it was built from smaller functions. This new function is just another standalone function that you can use anywhere, and you can build bigger functions from it. And the banana disappeared. That's a very cool thing. The smaller functions cared about the banana, but the bigger function does not care about bananas. And so that's a way of doing data hiding or abstraction. It means only the small pieces care about something, but the big picture doesn't need to care about those. Right. So when you build a really big application like a web service, for example, this is how it would look like. In a website is in fact a giant function. Something comes in, which is an HTTP request, and something comes out the other side, which is an HTTP response. So the whole thing is a giant function. Now, inside that function, you might have a bunch of smaller functions which are connected in various ways. And so inside, there's these pipelines of functions. Now, there is some branching, but notice that all the arrows go in the same direction. Something comes in, and it goes all the way through, and it comes out the other side. So that's a slightly different from object-oriented programming. The functional thing tends to be a pipeline with data always going in one direction. So that's the power of composition for functional programming. And I have a whole talk about that if you're interested. I'll happily share that with you later on. So this composition is so important that pretty much every tool in the functional programming toolkit is about making composition easier. So things like monads, the scary thing about monads, they sound like they're a scary thing. Monads are a way to make composition work, to make composition easier. That's all they are. That's why functional programmers use them. They don't use them because they sound cool or anything. It's just a specific tool that solves a certain problem. So any questions so far before I move on to the next step? I'm going to stop every 15, 20 minutes if anyone has any questions so far. And I guess the best way to do the questions is to put them in the chat, I think. And then that way nobody asks, and then
yeah, we will copy the question from YouTube as well, but
yes.
We don't have questions so far.
No, okay. No problem. Okay, well, I will keep going, and feel free to ask questions as you see things, and I'll stop again in 15 minutes or so. So the first tool is something called a monoid. Again, that sounds like a lot of jargon. And this involves mathematics. So I know some people are scared. So let me show you the kind of mathematics that I'm going to be using. This is 1 + 2 = 3. Hopefully that's not too scary for people. Here's another piece. 1 + 2 + 3 is the same as 1 + 2 + 3. And finally, 1 + 0 is 1, and 0 + 1 is 1. Okay, so that's the mathematics that I'm going to use. Hopefully that's not too scary for people. So what's interesting is mathematicians have a certain way of thinking, and they will look at this and they look for patterns. Mathematicians love to look for patterns. And so they might say, oh, this is an interesting pattern. We have two things and we add them together and we get something which is the same kind of thing. We add two integers and we get another integer. And you say, well, that's interesting. I wonder if there's any other things that work. Oh, yeah, that works for multiplication. You take two integers and you get back another integer when you combine them. What about strings? Well, if you have two strings and you combine them, you get back another string. Okay, two things, some way of combining them, and you get back another thing. And if you have lists, concatenation of lists, same. You start with two lists, you concatenate them, and you get back another list. Okay, so this is a pattern you see over and over again in all sorts of things. Now, what's interesting is that when you combine two things, you get back another thing of the same type, another integer. And because that is an integer, you can add something else to it. And that is also an integer. And because that's an integer, you can add something else to it, right? So what we've done here is we've turned a pairwise operation that works on two things, and now we can make it work on lists of things. So that's a very cool thing. As long as it returns the same kind of thing, you can keep going and going. Just like Lego, you add two Legos together, you get a bigger Lego. You add two integers together, you get a bigger integer. And because of that, you can keep going and going. You don't have to stop. Right, now what about this other thing where you can combine them in different ways and it doesn't make a difference, right? So it doesn't matter whether you add 2 + 3 first or you do 1 + 2 first, you get the same answer. Now what's cool about that is because of that, all the different ways of combining them are exactly the same. You can take 1 + 2 and then 3 + 4, or you can do 1 + 2 and then you can add 3 and then you can add 4. They're all exactly the same thing. So sounds like it's kind of obvious for integers, okay? But it turns out to be a very useful thing. So for example, it doesn't work for subtraction. It only works for addition. Now this last one, 1 + 0 = 1, a mathematician would say, well, that's interesting. There's a special thing that when you add it, it does nothing. It leaves it alone. It just gives you back the original thing. So in case of addition, if you use 0, if you add 0 to anything, you get back the original thing, as if you never did anything. Okay, so that's a nice pattern. And for multiplication, the thing that does nothing is 1. When you multiply something by 1, you get back the same thing. Okay. That's the special kind of thing. And for strings, when you concatenate strings, the special kind of thing that does nothing is the empty string. Add an empty string to anything and you get back the original string. And for lists, it's the empty list and so on and so forth. So here we go. Here's our pattern that we've noticed. We've got some things and there's some way of combining them 2 at a time. And there's a rule that if you combine 2 things, you get another one of those things. And then also when you combine them, it doesn't matter which operation you do first. And finally, there's this identity element that there's a special 0 or 1 that when you add something to it, it doesn't do anything. So, okay, this sounds very mathematical. Why is this any good for programmers? You know, these 3 things, when you have this thing, this set of things, that is called a monoid. So the jargon word, the mathematical word for this thing is a monoid. Right. So it's jargon. So why is this useful as a programmer? Why should you even care about this? Well, the first thing, this thing, when you add 2 things, you get another one of the same kind. That's a way of turning a pairwise operation into something that works on a list, right? So, for example, if I want to say 1 + 2 + 3 + 4, right, that's a pairwise operation. Now, in a monoid, the way of applying it to a list is called reduce. So I can take a list of things and I can apply plus to every single element, and that's called reducing using plus. So I can work an entire list, okay? I'm going to use this a lot in programming. Again, if I want to multiply a list of things, okay, I've got a pairwise operation. I can reduce this list using multiplication. Or if I have a bunch of strings, a list of strings, and I have a way of combining them in a pairwise, 2 at a time, I can reduce the entire list using the same operation. So I can work on lists rather than individual items, okay? Now, so that's the benefit of this combining thing. Now, the benefit of the not caring about the order, the associativity, lots of benefits. The first one is divide and conquer and parallelization and incremental accumulation. I'll talk about parallelization for a second. So let's say that adding numbers together is really expensive, and I need to have big computers to do it. Now, obviously, adding 2 numbers is not complicated, but sometimes it is complicated. So what I can do is I can do 1 + 2 on one computer, and I can do 3 + 4 on another computer, and I can combine the results. So I can actually do, by splitting the operation and sharing it into lots of different computers, I can actually make the whole operation go a lot faster. And that only works when you have this ability to not care about which order you do things in. So if you want to do parallel stuff, monoids are great. Now, another useful thing, even if you're not doing parallel stuff, this incremental accumulation is really good too. So let's say that I calculate 1 + 2 + 3, which is 6, okay? And then the next day, someone says, oh, can you add 4 to that? And you have to say, well, I have to start all the way from the beginning. I have to do 1 + 2 + 3 + 4. Well, no, you don't, right? You don't have to start all the way from the beginning. You can start with what you've already done and just add the extra 4. You've already know what 1 + 2 + 3 is. You can just add 4 to that. You don't have to start from scratch every time. And that is also a benefit of this fact. The order in which you do things doesn't matter. So, you know, if you're doing incremental, if you've done a lot of complicated calculations and you need to do one extra calculation, you don't have to start from scratch. You can just do this one extra calculation on top. Now, the last one is if I'm doing something with an empty list, if I want to do something and I don't have any data, if I want to reduce a list using plus or something, but I don't have anything in my list, or I have some sort of divide and conquer algorithm, but one of the steps is missing. How do I do that? How do I work with that? Well, that's where the empty value is very useful, the identity value, the 0 value, because it's the place when you don't have any data, it's a place where you can start from, because you start from there and you add something to it and it doesn't make any difference. So it's always a good starting point. So the benefit is an initial value for something, right? So let's look at some real code. Let's say that I have a very simplified order line for a product or a website, and how much am I buying, and what's the total price. And I have a bunch of these things and I want to add them all up. Well, you could write a special loop that adds them all up, fine. But let's use this monoid idea to make our code more generic, okay? So here's a bunch of the lines I want to add up. So each one has a quantity and each one has a total price. Now, how do I add them up without writing a special loop? Well, I'm going to use the monoid idea. So what I'm going to do is define a combining function. So to combine it, I'm just going to combine the quantities and I'm going to combine the totals and make a new line item. Right, so that's my combine function, and my identity function is just the 0, 0 for both. So now I can, if I want to add them all up, I just say reduce the entire list using this combine function, and it'll do the whole thing in one step. And if I have a new one in my list, I can just use this extra one without having to recalculate the entire price over and over again. So that's a kind of very simple example of how you might use a monoid to do real code. Now, something which is very common is you have things which aren't monoids and you convert them into monoids. So let's say I have a bunch of customers. Well, customers, you can't really add customers together, right? Because they're not integers, you know. But what you could do is have something which is like customer statistics, like the total amount of money they spent or the number of orders they've made or the time they've been using. I don't know, whatever the various numbers. Now, those numbers can be added up because they're numbers. So it's a very common thing is to turn something which isn't a monoid into something which is a monoid. And the word we use for that, we're going to use the word map, and we'll come back to map later on. So map is a transformation from a non-monoid into a monoid. Now, once we have it into a monoid, we can then use this reduce function, collapse everything down to a single total. So that's map followed by reduce. So if you've heard about map reduce as a technique, this is exactly what it is. It's just it's something from functional programming. So map and reduce is basically falls out of using this kind of approach. Here's an example. It's a funny example of using map and reduce. If you have a sandwich, you can't add a loaf of bread and some lettuce and an onion. You can't add them together. But if you slice them, if you slice each one separately, you can add the slices together. So that mapping is converting the loaf of bread into the slices and the onion into the slices. And once you've got the slices, you can combine the slices together. So there you go. There's a kind of funny version of that. Right. So let me just do I think I might or might not do demos depending, but I just want to show you maybe how this works in real code. So I will start with, this is some F# code here, and you don't have to worry about F# too much. But basically, this is a kind of F# version of an interface. So this is an interface. Now, this is generic. So you combine two things to make a new thing, and then you have some identity thing, which is a 0 thing. So basically, you just implement this interface for the different kinds of things you want to do. So, for example, to add two integers together, I can say, well, to combine them, use plus, and the identity is 0. Or if I want to multiply them together, the combining thing is multiplication and the identity is 1. Or if I have strings, I can combine them with plus with strings, and then the identity is an empty string and so on. So once I've done that, let me just pull this down here. I'm not going to show you all the code because you probably don't care. But here's a list of numbers, and I'm going to use monoid reduce, and I'm going to pass in the add monoid. And it says the answer is now 55 down there. But if I want to use the multiply monoid, okay, I take the same list of numbers, I'm going to reduce them using the multiply monoid, and I'm going to get a different answer, which is a much bigger number. Or here's a list of strings, and I want to reduce them, totalize them using the string monoid, and there you go. I get the concatenated string. So there's an example of monoid is really just, you can in code point, it's really kind of an interface you implement. So here's my example that I had on the screen. Here's a record with two different fields in it. Here's my code that combines them together. And here's my identity version. So I'm going to say this monoid I'm going to use the combine function up here and the identity function up here. Okay, so I'm basically implementing the monoid interface for my special order line. So this is the amount of code I have to write. But once I've written that code, if you give me a list of things like this, I can reduce the entire list using my new personalized monoids that I created, my implementation. So it's the thing is, this is a pattern that you will see over and over again. The reason why functional programmers like it is you don't have to write loops. Once you know that this pattern exists and you see it over and over in your code, it's just something you reach for every time you want to combine things together. So that's that. Any questions so far? Any more questions?
Yeah, I don't see any question.
Okay. All right. Very good. Hopefully this is making sense to people.
Yeah, I think so.
It's. I know it's.
Yeah,
it's a bit.
Just a quick question.
Yes.
In C#, this is the aggregate method of link you, right? Or yeah.
Yes, it's exactly in C#. This is aggregate exactly.
Okay, and to create that kind of interface in C#, how it can be done?
Yeah, you could basically. I mean, in C#, this would be an interface. What I've gone here, this is the kind of F# version of interface. In C#, you'd basically define, an I monoid, and it would have. Let me see. It's hard to do the C# code in the middle of S#, but an I monoid, and let's see, it would return of type. Now in C# you don't use the tick A. Tick A is the F# way of saying it's generic. So it would be, and I can't remember how to do it in C#, but it would be something. It would be something like this.
Yeah, using an interface and generics, right?
Yeah, it would be some sort of generic interface, and it would be. I guess it would just take. It would take an A and an A, and return an A. Yeah, something like that.
That's the closure, right?
Yeah. So, and in C# you wouldn't. In F# we tend to use A, and in C# you tend to use T. So here it's the same type T. Whoops. And in fact, it doesn't need to be a function like that. Something like that. Yeah, you can't. I don't. You can have it. You'd have to have a get property or just a thing. So basically, you'd pass this piece. You implement this for your different things, and you pass this in as an extra parameter to anything that uses a monoid. So yeah, it's like I say, you could use. It's language independent. This is just kind of a pattern that you could use when you're doing anything. Now in C#, the aggregate function basically has this as separate parameters. I think in the aggregate in the C# link.aggregate. System dot. See, I don't use. It's a static member on aggregate. Here we go. So yes, it takes a function and a seed, what they call the seed. What I'm calling the identity element is what they will call the seed. And the combining function is what they call func.
Okay.
So this is a function that takes an input and an output, two inputs, and returns a new one. So it's very similar.
Yeah.
So okay. Right. Someone said, how do I do this in parallel? I'm not going to really show you the parallel stuff, but you could totally have a parallelizable thing that you pass in a monoid, and it can combine them in different orders. but I don't have code to demonstrate that. And to be honest, that's a bit over. To be honest, the parallel thing is a bit oversold. I almost never do parallel programming. Much more useful is the incremental side of things for monoids. Right. So here's the thing: when you know about monoids, you start seeing them everywhere. You start looking at everything and say, hey, that's a monoid. So for example, in metrics, if you're doing, you're having logging and metrics, you want to keep track of things. There's a classic thing about use counters rather than rates of change. And in a monoid model, you just say, make sure your metrics are monoids, right? That means that you combine two and get another metric, and that you have a 0 metric for when you have missing data or when you're doing incremental updates. Once you understand what a monoid is, you can a lot of things just become a lot simpler. And there's a lot of design patterns. Mark Seaman had a whole blog about this. The composite design pattern, where you combine two things to make another thing, right? That is a monoid. The null object pattern. So the idea about that is rather than having a special, rather than working with nulls, you have a special object that doesn't do anything. That is a monoid. That's the identity of a monoid. You can add a null object to a normal object. You can combine them, and it still works. Composable commands is an example of a monoid. You combine two commands to get a bigger command. That's a monoid. And in domain-driven design, there's this idea of closure of operations, that when you combine two things, you get another thing of the same kind. That's a monoid. So you start seeing these things everywhere once you get this in your head. Now let's look at function composition quickly. Function composition is combining two things to make a bigger thing, right? Is that a monoid? The answer is no, because it's not the same thing. One of the things was an apple to cherry, an apple to banana function, and the output is an apple to cherry function. So that is not a monoid. However, if I had everything where everything was an apple, so this is an apple to apple function, and this is another apple to apple function, and I combine them to get an apple to apple function, that is a monoid. So certain kinds of function composition can be treated as monoids as well. So like I say, you start seeing this everywhere. So that's good. Right, so monoid is a set of things and some way of combining them. And there's lots of different words, like you say, I mean, I'm using the word combine. String concatenation is a kind of monoid thing, adding things together. Sometimes you see in functional programming, you see weird symbols with angle brackets and plus signs and stuff. Those are all ways of combining things together. And there's some rules like the closure rule and the associativity rule and the 0 rule. When you have these three rules, you've got a monoid, and once you know what's a monoid, you don't have to describe it anymore. Everyone knows what you can do with it. So it's really good for reducing a list of values to a single value. It's good for doing parallel calculations, and it's good for doing incremental calculations. So, right. Now, the next thing I'm going to talk about is effects. And functional programmers use effects, the word effects, a lot. So what is an effect? Okay, not a side effect, but an effect. So effect, from a programming point of view, is just some sort of generic type. It's like a list, or it could be a type with extra data, like an option type or a result type. Or it could be a type that changes something, like the task type or the async type or a random type. Or sometimes you have types that have state. They keep track of their internal state, like parsers and stuff like that. So these don't really have anything in common. They're all just really kind of generic types. So that's really what an effect is from a functional programmer's point of view. It's just something more than just a regular type. Okay, so it's kind of vague. Now I'm going to focus on three specific ones, which is list, option, and async. Now async is an F# type, but if you're a C# programmer, you can think of it as the task type. Async and task, from our point of view, they're basically the same thing for the purpose of this talk anyway. So they're completely different, but you'll see that we can use the same pattern on them over and over. The same approach of solving a problem, even though the types, even though they're used in completely different ways, the way of solving a problem is the same for all three. So one thing I think might be useful to understand is the way that there's this kind of parallel world. There's a normal world with normal strings and normal things in it. And then there's a kind of parallel universe, an effects world. Right, so here's a normal world, and there's a string, and there's an int, and there's a boolean, and there's functions that turn ints to strings, and there's functions that turn ints to booleans, and so on and so forth. Right, so this is kind of the normal world of things we work with as programmers. Now, if you think about the option effect, if you think of it as an effect, it's a parallel universe where instead of having strings, you have options of strings. And instead of having integers, you have options of ints. And instead of bools, you have options of bools. And instead of functions that turn ints to strings, you have functions that turn options of ints into options of strings, right? So everything's kind of just like the normal world, except that everything is turned into options, right? So I'm calling this option world. Now there's another corresponding list world, right? So in this world, instead of having strings, you have lists of strings. And instead of having ints, you have lists of ints and lists of bools. And all the functions turn lists of ints into lists of strings, or lists of ints into list of bools. Everything works on lists, right? That's list world. And you could have async world or task world, where everything is tasks or asyncs, and all the functions work with asyncs or tasks, right? So it's the same idea. We have this kind of parallel universe, which is based on the normal universe, but everything is transformed somehow into a list or an async or whatever, right? So in general, there's some sort of effects world, and there's some sort of generic type E, and everything in this world is an E of something, and all the functions are E functions. Okay, so it's the same technique. Well, once we use it for one world, we'll be able to use the same technique for all the other worlds. So how do you do stuff in an effects world? This is the challenge. So here's a real world example of a kind of problem that you might have. So this is my little scenario. You're going to download a URL, and it's going to have a piece of JSON in it. And then you're going to decode the JSON into a DTO object, like a dumb object, like a customer, for example. And then we're going to convert that dumb DTO object into a valid customer. So we're going to be doing validation and making sure that all the fields are correct. And then finally, we're going to store the customer into a database, for example. Okay, so very simple kind of operation you might write some code for. But it turns out to be quite tricky because of all these effects that kind of get in the way. So when we download the JSON file, we're going to start with a URL. That's just a string. So that's in normal world. But the output of that function that downloads the URL is going to be an async result. It's going to be a task, because it's going to be a background task, and it might not work. So it's going to have either it's going to be successful or it's going to have a failure. So that's what I call the result type. So it's async and it's a result. So it's not normal thing at all. It's this special async result thing. Okay. Now, when we decode the JSON, we start off with a JSON, which is a string. And then after we've decoded it, we have a customer DTO, except it might fail. It might be invalid JSON. So we're going to say that's a result as well. It might either succeed or it might have a failure. So we're going to use a result for that. When we take the customer DTO and we validate it, well, we can validate the individual pieces. We can say, is it a valid name? Yes or no. Is it a valid email? Yes or no. Is it a valid birthday? Whatever. All these different pieces. Now, each one of these pieces might fail. So we're going to use a result for those. Now, combining the valid pieces into a valid customer, that is all done in the normal world. So that's easy. And then finally, when we want to store a customer into the database, we start with a normal customer, but the function that puts it into the database, again, it's asynchronous, right? It doesn't return straight away. And secondly, that might fail too, because the database is unavailable, or it's a authentication error or whatever, various reasons why it might fail. So all these things, these are kind of, they're not simple functions, and it's very hard to compose them together, right? So if we look at the signatures, it says, you give me a URL, I'll give you an async of a result. You give me a JSON and I give you a result of something. You give me a DTO and I give you a result. And you give me a customer and I give you an async of a result. None of these functions can be composed together in a pipeline because the output of the first function is not the same as the input of the second function. And the output of the second function is not the same as the input for the third function. These things cannot be connected together, and that is a problem. And so that's what the functional toolkit is all about. It's making how can we use the functional toolkit to turn these into things that can be connected together. And that's what we're going to do in the rest of the talk. So lots of different effects here. So async results, result, another async result. These things are different worlds we have to work with. So how do we compose them together? We can't right now. They just don't fit. The inputs and outputs don't match up. So let's see if we can fix it. So we're going to start with options for starters. Now here's our world of normal values. And let's say we have a world of optional values. Now it's very common that when you write code, you go in, somehow you create an optional value. And then you need to work with that optional value. So you bring it down to normal world. And then that makes another optional value. And you need to work with that. And you make another optional value and you have the final result. So this back and forth between the worlds is a very common pattern. And I want to try and persuade you this is actually a bad pattern. Don't do this. Okay. What you really want to do is when you go into a different world, you want to stay in that world as long as possible. Try and do everything in that world and then only come down to normal world at the very end. And this is one of these changes in the way of thinking. This is the functional programming way of thinking, which is kind of hard if you're coming from object-oriented programming. So let me kind of give you an example. Let's say we have a very simple function that adds 42. Okay, that's my function. Now that works on a normal integer. But if I try it on an optional integer, that's an error. It doesn't work. It won't compile. Add 42 does not work on optional integers. So what's my fix? Well, the bad way of doing it is to write a special custom function that says, well, if it's some value, and by the way, if you're not familiar with options, you can think of them as like nullables in C#. So in a nullable, it would be, does the nullable have a value? If the nullable has a value, then I can use the thing. And if the nullable doesn't have a value, I ignore it, right? So if it does have a value, I can do the bit of function. And if it doesn't have a value, I can ignore it. And so what I'm doing is I'm basically unwrapping it, bringing it down from this effect world, doing my normal thing, and then putting it back up into effects world again. And again, this is a bad way to do it. So I'm coming down, doing my thing, and going back up. So we don't want to do it this way. Well, if we don't do it this way, what can we do instead? What we really want to do is do everything up here in the option world. But add 42 is not a function in option world. It's a function in normal world, right? We want to stay up here, but this add 42 does not work. So what we do is we move a function from the bottom to the top using map. And this is what the map function does. So here is our add 42. It's take any kind of function down here and we do map and it comes up into option world. And now everything in it is options. Remember how I said all the functions in option world work on options. All the functions in real world work on normal things, but everything in option world works on options. So this is a function transformer. It transforms one kind of the normal function into an option function. So if I do option map on add 42, that gives me a new function. And this new function lives in option world. And because it lives in option world, I can give it an option to process, and that works great. So that's what option map is really useful for. It's a way of transforming from a function down here into a function in a option world, or list world, or something else. Now, rather than writing a special intermediate function, we'd often just write it like this. We'll just do map straight away and not bother to have an intermediate function. So if you're in C# land, the map function is just select link.select, which is the same thing. It transforms some input list into some output list by transforming each element of the list. But this is not, the link one is really works for enumerables, right? This works for anything. It's not specific to lists or sequences or anything like that. It works for anything, I think. Right, let's look at a list world example, okay? So if I want to add 42 to each element of the list, well, what I can do is, create a new list, and for each item in the list, add 42 to it and put it in the new list and return the new list and write a special custom piece of code just to do this. And, that's not very good. I'm doing the same thing, right? I'm unwrapping it, I'm doing my stuff, and I'm wrapping it back up again. And I'm writing a special custom piece of code just to do this thing. And we don't want to do that. That's bad. Okay. So again, don't unwrap it and wrap it back up. We want to transform add 42 into list world. So we're going to use list map to do that. So any function in normal world can be transformed into a function in list world using list.map. So, and that's the same kind of thing, the same concept, even though lists and options are very different, I'm using the same idea of mapping. So if I use list.map on this function, I now have a new function that works on lists. And because it works on lists, I can pass a list in and get a list out. So that is mapping. Okay, and you can see how this affects idea. I'm using the same principle. This map idea is working for all sorts of different effects worlds. Now, a lot of people say, well, is this any better than writing my own loop? I mean, I could have written a loop in a couple of lines of code. And the answer is, once you see it, it's a pattern. Once you see this pattern, you start using it everywhere. And it is faster than writing your own code, because I know for a fact when I see list.map that, for example, it's got the same number of elements in the new list as the old list. It doesn't change the number of elements, right? And I know that the type of the input is the same as the type of the output. I mean, there's a bunch of things I can know just by looking at it. So unlike if I was trying to look at a hand-designed loop, I would never be sure, is it going to be filtering things? Is it going to be transforming things? What exactly is it doing? I have to look at the map. I have to look at the code. But this one, a map never filters things. Now, if I want to filter things, I use the filter function, which is the where, like in link, that would be the where function. So I know by using these patterns, I want to do a transformation, I use map or select. I want to do a filter, I use a filter or a where clause, whatever. Each is a special tool that I use to combine them together. And once I know what these tools are, it makes my code, I think my code easier to understand. Right. Here's the async world or task world. Okay. So I have a function that works in normal world, and I can have a function that works in async world or task world. So that's kind of nice too. And most in functional programming languages, almost all generic types have a map function that goes along with it. So try and use it wherever possible. And if you create your own generic type, create a map function for it as well, because it'll just make your life a lot easier. So any questions about that so far? Any more questions?
Yeah, we have another question here, but it's related to, I guess, from monoids and how to parallelize that. But it's
yeah, the parallel. I thought the parallel question from monoids. I'm not going to have time to go into. I won't. I can't answer that one. So.
Okay.
Yeah.
I have a quick question about, you mentioned filter.
Yes.
Or where, or this kind of I don't pattern. It's just for lists, right? So it doesn't apply for other.
Exactly. It doesn't work for everything, but this one, works for async. Yeah, filter only works for lists,
Okay.
but or enumerables. But this idea of mapping actually works for any kind of thing. Like I say, it works for things which aren't lists. So yeah, it's a very useful pattern.
Yeah, it's confusing in Linkio because you think that the select it's like the other ones, but then you don't.
Select is actually much more general, and in fact, you can actually. There are some things you can do with link where you can actually write special. If you write your own select extension method, you can use it for any type, and it will work, which is kind of weird. The link, the link stuff, it doesn't actually care about. It's not really just for lists. You can rewrite your own select extension method, and if you write a select many extension method, you can use the same link syntax to work with all sorts of weird types, not just lists and enumerables. So that's a kind of weird trick you can do in C#, which I'm not going to show you, but you can do that. It's monads. You can do monads in C#.
Oh, yeah.
Yeah. Right. Okay. So this is this whole concept of having these different worlds is something that takes a while to get your head around. But I say it doesn't work. It's not about a specific type. It's about a general pattern that works for any kind of generic type. So I think I won't do a demo right here. So the jargon word for this is a functor. That's the FP jargon. I find this a bit jargony. I just prefer to use map. Okay. So it's a functor is just some sort of effect type, like a list or an option or a task or something, or any of these things, and some sort of map function that transforms a normal function into this effect world. So that's all the jargon is. It sounds very complicated, but that's all it is really. It's more scary sounding than the actual thing. So just like when I had a monoid, I defined my own monoid. It's kind of an interface. I could define sort of a functor interface that would just give me the map thing, and I could use it anywhere. So in C#, select, sometimes you'll see it called lift. In C# and link, it's called select, and so on. So, right. Also, by the way, it has to have a sensible implementation. I mean, a map function that kind of throws an exception or does stupid stuff is not a very good implementation. So there are actually certain rules that it has to follow in the implementation. I'm not going to talk about it, but obviously it turns out there are some kind of standard rules that it has to follow in order to be a good implementation. Right. Okay. Now there's another way to move the things between worlds. So that map was moving functions between worlds. Now, sometimes you just want to move individual values between worlds. And let's say that you have an int and you want to make an optional int, right? So I'm going to call this return. It's often it's trivial that you don't even think about it. But I'm going to give it the generic name return for now. So for example, if I want to make an optional int, I just say some int. That's easy. So that's a value in normal world, and then it's now a value in option world. If I have a normal int and I want to make a list, well, I just make a singleton list, right? So that's a normal int, and that's a list made out of that int, or an array made out of that int. Right, so that's pretty easy. It's so trivial that it's not even worth thinking about as having a name, but it turns out it's an important part to use it in other kind of things. So I'm not even going to go into too much detail. Now here's a much more complicated one. Now we're going to come into monads. So there's a function. One of the really common problems you have is these world crossing functions and how to connect them together. And we're going to use bind for that. So what is a world crossing function? Okay, a world crossing function is a function which has something, the input is in normal world and the output is in a different world. So for example, returning a list of integers, right? The input is an integer, but the output is a list. So the input's in normal world and the output's in list world. Something that simple, right? That's in normal world and that's in list world. So if you can think of it like this in a diagram, it starts off down at the bottom and it goes up to the top. Okay, very, very simple. How about getting a customer from a database? You pass in an ID, for example, and if the customer's found, yeah, it's good. And if it's not found, that's an error. So you could say, you give me a customer ID and I might give you back some customer data. It's optional or nullable, depending on how you want to talk about it. So again, it starts off in normal world and the output is something in optional world. So this way of there's a lot of functions where you start off in one place and you move up in another place in the end. And this one is get customer. So even simple functions like getting a customer from database something are world crossing functions. So here's the problem. How do you chain world crossing functions together? Because they start off in one place and they end up over here and you can't connect them together. Right. So let's say I have a function that does something. and it returns an optional value. Well, I need to figure out, is it something or nothing, right? Or if if it's a nullable value, is it null or is it some value? So if it's something, I can do the next step. Okay, and if that's maybe optional, and so I have to check it again, and then I can do the next step. And if that's still good, I can do the next step. So you end up with this kind of horrible, ugly pyramid. You know, it goes in and in and in and comes out now and out again, right? Whenever you have these kind of world crossing functions, you get this kind of pattern. And this is often called the pyramid of doom. You have this nested stuff. Is it okay? Then I can do the next thing. If it's okay, I can do the next thing. If it's okay, I can do the next thing. So it's kind of this triangle shape of the pyramid of doom, it's often called. Now you could say, you know, that's one example. Let me show you, I think, an example of tasks, right? So you start a task, and when the task is finished, you want to do another task. And when that task is finished, you want to do another task. And when that task is finished, you want to do another task, and so on and so on and so forth. And again, you have these world crossing functions. It starts off with a normal input and the output is a task. And because of that, you have to do this really awkward chaining together by extra work each time. Right. In this case, it's callbacks. Depends on what it is, but each time you get this, definitely get this pyramid effect each time. So this is really ugly code. Everyone hates writing this ugly code. Right. So how can we fix it? So there's a pattern that we can exploit here. You see, if it's something, do something, otherwise do nothing. If it's something, if it's valid, do something, otherwise do nothing. If it's valid, do something, otherwise do nothing. It's the same pattern over and over again. So what we're going to do is turn that into a little helper function. Okay, here's our little helper function. Well, here's the pattern. If it's something, do something, otherwise do nothing. Right, so that's the pattern that we're going to see over and over again. Right, so let's turn this into a little helper function. Okay, so this is the helper function I'm going to write, called if some do. So if it's something, then do something, otherwise do nothing. Now, what is it we're going to do? Well, it depends. We don't even know what it's going to do. So we're going to pass in a function that says what to do, right? It's an extra parameter, which is a function parameter, which describes what I'm going to do with it if it's valid. So this is where we're starting using functions as a parameter to another function. Okay, this is where your head might hurt a little bit, but this is a very, very common thing in functional programming. I'm just parameterizing. I don't exactly know exactly what I want to do, so I'll just pass in a parameter that tells me what to do with it. Okay, so I'm parameterizing everything. Now this helper function, once I've defined it, it's really, really useful because I can go back to my original code and do something, and then I can say, if that's valid, do the next thing. And if that's still valid, do the next thing. And if that's still valid, do the next thing. And what I'm doing now is, instead of having this kind of nested deeper and deeper, deeper nesting, I now have a nice flat, straight line, which is a lot easier to write and it's a lot easier to understand. So this helper function is really, really useful for fixing this kind of problem. Okay, much cleaner code. So if you think about it from a railway analogy, instead of having a function which has one input and one output, we have a function with kind of one input that has two possible outputs, right? It's either kind of successful or it fails. It's either something or nothing. Right? It's either nullable, it's either null or valid value, whatever, different ways to think about it, right? And here's our problem. We want to chain these things together, right? If it's valid, we want to do the next thing. But if it's not valid, we want to bypass it. So if you think about, if you have a whole chain of these things together and you want to connect them all together, well, if you're doing railway, if you know how to use a model railway, you know how to make this, right? If you have a bunch of these things, you can connect them like this. So this is why I like the railway analogy, because it's kind of really obvious how to make this work. Now, here's the problem. Okay, so this is what we want to get to. Here's the problem. When you compose simple functions with one input and one output, it's easy to connect them together. You just connect the output to the input. If they have two inputs and two outputs, they're also easy to connect together. You just connect the green bit to the green one and the red one to the red one. But that's not what we have. We have this, where there's one input and two outputs, and they don't connect together. So that's a problem. So how can we combine these things that don't match up? And so the answer is bind. Bind is a special function or a kind of concept that we use to solve this problem. And so functional programmers love to use the word bind. They get very excited by the word bind. So here's what we start with. We have this one track input and a two track output, and these do not compose, right? Because they don't match up. Now, if we had two track input and a two track output, that would compose because we can just connect the inputs and the outputs, right? So the first one is no good, but the second one is good. So if we can convert the first one into the second one, we've solved our problem, right? How can we convert the first kind of thing into the second kind of thing? So let me show you. Again, using a little model railway, there's actually these little things you can get with a kind of a little slot that you put the track on top, right? You have like a two track thing, and there's like a slot on the top that you fit the other one onto. That's exactly what this is. There's a slot, you pass in the bad kind of thing, and after you've transformed it, it comes out as the good kind of thing. And that is the transformation. This is a function transformer. You pass in one kind of function which has a certain kind of shape, and it comes out as another kind of function with a different kind of shape. So that, if we can implement this, we've solved our problem. So let's see how we can implement this, right? Well, it's actually really easy. It's actually 4 lines of code. It's much more complicated to explain than it is to actually write the code. The code is like very simple. The code says something comes in and you just check. You do a pattern match or a switch, depending on which language you use. But you say, well, if it's the first kind of thing, right? If it's the first kind of thing, we just call the next function. And then we're done. And if it's the error track, we just ignore it. So we've turned, by writing this function, we just turned the bad kind of function into the good kind of function. So let's use this to chain the options together. Okay, this is what we had before, where we had this kind of nested, getting deeper and deeper nesting. And if we use option, we're going to define bind like this, which is what I just showed you a minute ago. And what I've done is actually, it's not obvious, but this is actually exactly the same function that I defined earlier. Last time I called it if something do, and it's actually bind. It's the same thing. So there's lots and lots of different names for this concept, but the concept is the same across all the different patterns. So I'm going to call this bind from now on. So you pass in with bind, that's the next function to call. That's the parameterized thing. And then once I have that implemented, I can go and write my code using bind. So it's exactly the same as when I had my if something do. But rather than having a special case, I now have a generic approach that works for all types of things that I want to work with. So I can use bind for options, I can use bind for lists, I can use bind for async, I can use bind for result, and so on and so forth. So bind is a way of combining functions without having any kind of weird pyramids. So that's why bind is really, really important. Now let's use the same approach to chain tasks together, right? So I have a task, and when it's finished, I want to do the next thing. And if it doesn't finish or it throws an exception, something, I want to bypass everything else. So again, you can think of it as the kind of railway idea. And I write a special, if I'm doing it the ugly way, I have to like have a nested handlers for each thing that happens and wait for it to finish and do the nested thing more and more deep. And again, it looks really ugly to do it this way. But if I write my little bind function for tasks, which says when it's finished, do the next thing, right? When I've written this little helper function, again, and I parameterize what is the next thing, well, I don't know. I'm just going to call it some sort of function. When I do that, I can rewrite my code to use this nice straight line, no nesting. And let's look at error handling. Let's look at one more example of error handling. So here is some C# code for updating a customer. And for example, you might say, well, I get a customer, I get some data in and I validate it and I lowercase the email and I update the database and I do all these things. And it looks very nice. But as soon as I start adding error handling, like what happens if it's not valid? What happens if I can't find the customer record? What happens if the database throws an error? What happens if I can't send the email? All this stuff gets more and more complicated. So error handling tends to make your code look really ugly and really messy. But it's really important to have error handling, but it also makes your code look ugly. So how can we fix it? So, you know, this is like 200% extra codes, and this is very typical for any kind of code which does error handling. So let's look at the functional approach to doing this, which is to use a result type. So a result type is basically a type with two parts. It's either success or failure. It's two choices. So when you validate something, it's either a success or a failure. And in F# we'd write it like this. It's like, you can think of it as like two different subclasses if you want, or you can think of it as two different values within a tag or whatever. Those are different ways of implementing it. But basically there's two choices, either okay or it's an error. Okay. Now, once we have this thing, when we write our code, when we validate something and say either it's an error or it's another error or it's okay. So basically all our code starts looking like this. It's either successful or failing. And when we write code this way, we end up with these tracks that look exactly the same. The input comes in and it might succeed and it might fail. And we want to connect them up into a railway like this. And we're going to do exactly the same thing we did before. We'll write a special kind of bind function that allows them to be connected. And this is the two-track model of error handling, which I call railway-oriented programming. And what's nice about this is that your code looks very clean. So if I was writing it without doing any error handling, I might write code that looks like this. I might say, you know, receive the request, validate it, canonicalize it, update the database. And if anything goes wrong, I'm just going to crash. Okay. So, you know, that's nice, clean code, but there's no error handling. Now let's add error handling into this code. Okay. Because this is like one track, no error handling at all. So let's write the error handling version of this code. So the error handling version of the code looks exactly the same, which is very cool. Now I'm cheating a little bit because it's not exactly the same. It just looks the same. But what's actually going on behind the scenes is it's got this two-track model. So each of these functions here, each of these steps is actually not a one-track step, it's a two-track step. And so each of the things we do is actually handling the errors nicely, but because I'm using this two-track model, I can connect them together in such a way that they look like it looks clean. It still looks nice and clean. And I don't have my code being messy and ugly with all the error handling in it. Right. So this is why bind is so important to functional programmers. It makes these world crossing functions possible. Okay. So here we have this world crossing function. It starts off in normal world and it ends up in effects world. And, you know, actually that's before we start binding it. But as soon as we do a bind, it kind of transforms it into a horizontal function where everything is in effects world. And remember I said, it's really nice if we can live in effects world. Everything we do is in one place. We don't go back and forth between these worlds. We stay in one world all the time. And that's what bind does. It converts this world crossing function into a function that works in horizontally in one world. Okay, so bind, this is why bind is so important. So if you think about it, you often have this situation where you have a function down here and it goes up, and then another function down here and it goes up, and another function that goes there, and these can't be connected. But if we use bind and we transform them into horizontal functions like this, then they can be connected in a nice line. So that's why bind is so important. Okay. So that's the importance of bind. I've got a question which I'll answer in a minute. So this is the most important word in functional programming, monads. Okay, so now you know what a monad is. A monad is just something which has binds. Okay, so you can see why monads are so important because they allow you to connect things together. So a monad is not just the bind function, it's actually some effect type like optional list or async, some sort of generic type, plus two functions, a return function that takes you from down there to up there, like we saw, and a bind function that converts a diagonal function, a world crossing function, into a horizontal function. So that's what a monad is. And again, there's some sensible rules about sensible implementation called the monad laws. Now, the word bind is often has many different words, like in C#, we select many. In other languages, it's often called flat map. In Haskell, it actually has a special symbol with arrows and stuff. So there's lots of different words for the concepts. So I'm just going to use the generic concept of binds to represent this. But this is why monads, this is why functional programmers go on and on about monads all the time, because it allows them to chain certain kinds of functions together very nicely. The railway-oriented programming approach is monads. And you can see it makes things, rather than having these horrible pyramids, nested things, as soon as you use a monad or as soon as you use bind, you get a nice linear, straight line. Everything looks much cleaner, a lot less messy. So that's why functional programmers love monads. So now you can talk about monads to your friends and tell them how good they are. So if you want to chain these kinds of effects generating functions, use a monad. Right. If you want to bring results to C#, are you creating an anti-pattern doing the wrap of everything in a new object? I think you're referring to this thing when I'm coming down out of effects world. I have to go back up here a bit. Let me go out here. I think yeah, I think this one. So this thing of coming out and going back up again is an anti-pattern, yes. So you want to try and stay horizontal up here and use the map. In this case, I was using map. I think that was the question. And yeah, so wrapping things in a new object. Well, okay, so if you think about, I'm not quite sure what the question is, whether it's to do with that, whether it's to do with the memory allocation. Yes, you will be generating a lot of new data. Everything in functional programming is immutable in general. And so, yeah, you'll be creating new objects over there. You're not reusing the same list. You're creating a new list, which is what C# does when it does select. It creates a new enumerable. It doesn't update the original enumerable. But if you want to give me some more details than that, I'll try and explain that in more detail. Right. Any questions on monads? So I know this is a lot to understand in a short period of time, but hopefully you can see why monads are so important. Now, exactly how you use them in practice is a bit trickier. And it takes a while to get your head around them, but you can see, hopefully you see they're not scary. It's just a technique. It's just a tool that you use in a certain situation when you want to solve a certain kind of problem. Any more questions before I move on?
Yeah, someone, well, in YouTube, someone was commenting that you can do railway-oriented programming with extension functions in C#. Just to see what you think about that.
You can do you can do railway-oriented programming in C# if you want to. My only concern about doing that kind of thing in C# is that a lot of other C# people will not understand what you're doing. So one of the things about using a functional language like F# or Haskell or ReasonML or Elm or something is that you can pretty much assume that anyone using that language will understand the techniques. In C#, I would probably stay away from doing a lot of functional programming just because most other C# programmers are not that familiar with the techniques, and therefore they would probably look at your code and not understand why you're doing it that way. Now, if you're working with a team of other functional programmers, that's fine. But if you're working with a bunch of object-oriented programs, I would try and write code that other people can understand. But there's nothing stopping you doing this in C#. No, absolutely. There's a bunch of libraries for C# that have these tools built in, monads and stuff built into it. There's one called Luthi. I can't remember, but if you just Google functional programming libraries for C#, you'll find all sorts of cool libraries. But how to use them this is where this toolkit comes in. You have to understand how to use them in different situations and what tools to use in which situation. Right, I'm going to move on. If there are any more questions, do interrupt me if you've got more questions. Right, one quick question. People say, what's the difference between a monad and a monoid? Because they both sound like they're the same thing. They're not the same thing. The monad is the thing where it's for chaining together functions, and a monoid is the thing where you can combine two things to make another one of the same thing. Yes, the Luthi language extension, that is the C# functional library, which is quite good. Okay, so monoids versus monads, they're not the same thing, and they're not used in the same way in functional programming. They solve different problems. However, if you think about, there is that kind of connection, which is something called Kleisli composition. I'm not really going to get into it, but if you think about these railway tracks, you can combine them, rather than converting them into two tracks, you can actually combine them into the same shape, right? If you think about it, I don't really have the pattern, but you can see that if you connect the things together, you can make a new piece of track which has one input and two outputs. So that's an example of composing two pieces of track to make another piece of track which has the same shape. So that sounds like a monoid. So it turns out there is a way of combining two things to make the same kind of thing, and it's called Kleisli composition, and it has a weird symbol. And if you see that kind of thing, that's what's going on. So again, you can add more and more things. So this is kind of the monoid version of function composition for this kind of situation. So, and again, it doesn't matter which order you do it in, and there's an identity element. So it is a kind of monoid, but that's just showing you that it's kind of, there's a relationship, but it's not really that useful. Right, I'm not going to show you Kleisli composition. Okay, final tool is combining things in parallel with applicatives. So often you have two things wrapped in an effect, and you want to combine them. And like you have two options and you want to make a bigger option out of both of them, like, you know, an int and a string or something. Let's say you have one of them is missing, then the whole thing is missing. You have two lists and you want to combine two lists. There's actually two different ways of doing that. You can do a cross product where you combine each element in pairs, or there's another way which is typically called zip, where you combine the first element of each one and the second element of each one and the third element of each one. But anyway, it's a common problem. You have going to combine the results of two different things, and that's we're going to call this thing applicative functors, another piece of jargon. Okay. So again, it's got a bunch of code. I'm not going to go into this. I'm going to skip over this. Why is this useful? Okay. The reason it's useful is when you want to do, especially things like validation of things in parallel. So here we have a customer record, and there's a name, and there's an email, and there's a birthday, and they all have validation logic, right? Each field has to be validated. So we create these validation functions, like the name, validating the name, validating the email, validating the birthday, and each one of these functions has one input, and the output could be success or it could be a failure. So there's like two different outputs, two choices of output. Right, so we have this kind of the same kind of railway track that we've been looking at before. Now, here's the problem. If we chain them together like this in a row, then when something goes wrong, we only get the first error. Like if the name is invalid, we never get to validate the email. So we never get a chance to figure out what the email, you know, it skips the rest of the validation. And sometimes that's what we want, but especially in validation, that's not what we want. We want to get all the validation at the same time so we can, you know, update our data, right? So that's the problem when we do things, when you connect them in a row like that. So what we really want to do is do each validation separately and then combine the output into a single thing. So we're doing kind of think of it as kind of doing it in parallel. We do each of these things independently and then we combine them. And that's much nicer because we get all the errors together. So how do we combine them? Well, here is the individual validation functions go from normal world up to result world. Now we have a function that will make a customer from the individual pieces, but it only works with normal values, and we don't have normal values. We have result values, values that could be an error, right? So what we do is if we can transform our normal function into the result world, we can combine the values in result world. I'm not going to really get into it. It's too complicated to really explain and too much. But the point is, it allows you to combine things in result world to make another thing in result world. So, which is exactly what we want for things like validation. And so these functions are normally called lift functions. There's like one for each parameter. There's a 2-parameter one. There's a 3-parameter one. So a 2-parameter one would turn a normal 2-parameter function into a 2-parameter function in result world. And there's a 3-parameter one and a 4-parameter one and so on. Let's see, here's the 3-parameter one. It turns a normal 3-parameter function into a 3-parameter function in result world. So just kind of like map, but kind of more with more parameters. Right. So let's say that I want to, let's actually look at some real code. Let's say I have a DTO, which is an unvalidated data structure with just regular strings and so on. So I validate each part. I validate the name and I validate the email. Now, each of those pieces is either a name or an error. It's not just a regular name. So I can't just stick them straight into a data structure because I have to find out whether it's valid or not. So I use this lift function and I convert it into a result world lift function, and then I can pass in these 3 parameters. And now this is where people are probably going to get very confused. And I totally understand why this is going to be confusing. So I'm not going to really go into it, but I just want to show you there is a technique for making validation work in a few lines of code. So this is like 6 lines of code or 7 lines of code, and it does validation very nicely without any kind of exceptions, without any weird stuff. It's a nice technique for combining things. Right, so there's the magic happening, and I'm really, like I say, I'm not going to explain how it works in too much detail, but it's just something to know about. So I'm going to skip the demo. Okay, so let's review the tools. We've got this combine, which is combining 2 things to make another one. That's monoids. Reduce, which reduces a list of single value by using combine. That's also a monoid kind of thing. We have a way of mapping functions into an effects world. We have return, which turns normal things into an effects world. We have bind, which converts diagonal functions into horizontal ones. We have apply and lift and so on, which combines things in parallel. So we have, our toolkit is beginning to grow. We have like 6, 7 things in our toolkit already, right? And this is actually pretty much all the tools we need. There's only a few more that we need to get everything we need. So this is our toolkit. Now let's use them all together to solve the original problem we had of downloading some JSON. Okay, so this is let me just repeat what we had. You're going to download a URL into a JSON file. We're going to decode the JSON into a customer, DTO. We're going to convert the DTO into a valid customer. We're going to do validation on it. And we're going to store the customer in a database. So again, to revisit, we started with a regular URL, and the output is in this async result world. It's in a completely different world from the input. So this is a world crossing function. Okay, so we're going to be using the world crossing function technique on this, which is bind. Decoding the JSON. Again, the input is just a regular string, but the output could be an error, right? So it's a world crossing function. Validating the individual fields. These are all world crossing functions. Combining the fields into a record, that's just a regular piece of code. There's nothing special there. And then storing the customer in the database. Again, we start with a customer and the output is asynchronous and it might fail. So it's an async result. So let's use our toolkit to fix this up so we can actually work with it. We have the tools, we have the technology to compose these functions together using nothing but the toolkit we've developed. So validating the fields. Okay, we've got some validation functions and we want to create a customer. Well, we can do this part, the second part, using the lift function, the applicatives that we talked about. So we can just use our lift toolkit, the tool from the lift tool, and that will solve that particular problem. Now, this customer DTO to a customer and these two things, they don't compose, right? But if we use bind on both of these things, right, these are world crossing functions. If we do bind on both of them, they now live up in this world. So they're now all in a row and we can combine them together into one single function, right? So now we have a function that gives me some JSON and it gives me back a result. So this is what the code looks like. You give me some JSON and I'm going to do a bind and I'm going to do another bind. So it's more complicated to explain. It's actually 3 lines of code. Once you know how to use this toolkit, the amount of code you have to write is very, very small. But understanding why is more complicated. But the actual code you write is very small. Right. It takes much more time to explain it than to write it. Right. Now, this function as currently lives in result world, and we want to have it live in the purple world at the top. So we're going to use map. We're going to lift the whole thing up to there. So it starts off down here and it goes up there. So we're going to use map. And the last one, where we're storing the customer in the database, that's a world crossing function. It's a diagonal function. But if we use bind, we can make it go horizontal. We can go from there to there using bind. So now that's pretty much everything, okay? The first one goes up to there. The second one is also in purple world, in async result. And the last one, we also converted into the purple world. So these are all living in purple world, in the async result world, and we can combine them together into a single function in a single row, and that makes one overall function. So the whole thing can combine into a single function. So let's look at the actual code. And again, don't worry about this code in detail. I just want to show you this. It's more complicated to talk about than to write. It's literally a few lines of code. So there's one piece of code, is 3 lines of code. And then here's the overall function. Start off with the URL, download it, turn the JSON into a customer, and then store the customer into the database. And there's a map there, and there's a bind there, and there's various other bits in there. But the whole thing fits together very nicely once you know which tool to use. So that is basically how you would use the functional toolkit to solve a real problem of combining different kinds of functions together. So it does take a while to get your head around them. I know these are all kind of strange if you're used to object-oriented programming. But I think hopefully you can see that, first of all, they're not scary. They're just unfamiliar. They're something you're not used to, maybe. But you can see that you could learn about them. Then just because they're called monads doesn't mean they're too scary. And the second thing I hope you can see is that if you did learn about them, they're quite powerful. You can actually use the same 5 or 10 tools to connect different things together in a way to make them all fit together to write programs. So fitting the things together using this Lego composition, if you have the toolkit, you can pretty much make any kind of thing fit together with any other kind of thing and make bigger programs out of it. So the final program is, not that big. It just understanding why you would use bind and why would you use map, and that takes a bit of understanding. But once you know how to use them, putting them together is pretty straightforward. So I will do a quick demo and then we'll finish up. So here is the toolkit. Right. Just to show you this is a real thing. So just start off with this. Okay, so this is our name and our email and our birth date and our customer. So that's our kind of core code. And here's all the different kind of validation errors we can have. And here's all the different things we can have in the workflow. We can have a validation error, we can have a database error, we can have an email error, and so on. And here's the validation for a name. So if the name is blank, that's bad. If the name is too long, that's bad. Otherwise, the name is okay. And the email address, if it's blank, that's bad. And if it doesn't contain an @ sign, that's an error. Otherwise, it's okay. And the birthday, if it's less than now, it's good. But if it's older than now, that's an error, and so on and so forth. So that is our kind of core business logic, right? So that's our kind of core logic. And now we have to figure out how to connect them together. So this is our JSON object, our DTO. Notice there's no validation. Everything's just a string. Even the date is just a string. So everything, they could be null, they could be bad, all sorts of things, they could be bad. So here is our basic steps, okay? Downloading a file, you give me a URL and I'll give you an async containing a result containing a JSON. And decoding, all these things do not connect together. They have a regular, an input in normal world, but the output is in some ugly thing. It's like it's wrapped in a result, it's wrapped in an async, and they just don't fit together very nicely. Right, so now we do the implementation. So here's the implementation of downloading a file. It's just going to say nothing because it's a dummy implementation. Here's the decoding. I don't want to write a JSON decoder, so that's my JSON decoder right there. So don't worry about that. But now this is the actual logic for validation. Okay, so I have my little, I create a helper function. I validate the name. I validate the email. I validate the birth date. And then I use my lift function and I pass in those 3 parameters, and that is my answer. So my overall validation logic is like, what, 12, 15 lines of code. So that's that's actually what real validation code looks like. Notice it's nice and clean. There's not a lot of ugliness. I mean, there's a kind of duplication for every possible field. There's a bit of work, but it's very clean looking code. Okay, storing the database. I don't want to write a real database, so that's my database logic. Right, so this is my combining. This is my another little helper function which combines 2 things. I don't care about how that works. Right, here's my main code. You give me a URL, I download it, I process the customer, but this is not an async, so I need to use async map to turn that into an async. And then this is my diagonal function, and that doesn't work, so I'm using bind to convert it into a horizontal function. So that's my overall function, and it works just fine. And I don't have an example, but anyway, so that's how you'd write. So my overall code, again, it's just a few lines of code, but it's knowing which one of these tools to use, whether to use async map or async result bind. That's what you have to learn, which tools to use. But the overall code looks quite small once you understand how it works. Right, okay, so that is, I think I'll just finish up and then we can have questions after. So hopefully this jargon, this functional programming jargon is not that scary. Monads and monoids and functors and stuff, they do sound weird, but they are weird. But once you get the hang of it, it's not that hard. It's no harder to understand than all the object-oriented stuff. So, and the other thing is, you can see why monads are useful, why people go on and on about monads. It's for connecting things together. This is very generic. Notice this was nothing, these toolkits was nothing to do with a particular type, like a list or an option or something. It was these are conceptual toolkit where it works for tasks, it works for lists, it works for options, it works for, all sorts of different kinds of things. The same ideas of using bind and map and stuff on these things to solve problems. So these 11 or 12 functions we use over and over again in functional programming once you understand how they work. So map, apply, bind, hopefully when you see them now, you'll understand what they're being used for. And as I said, yeah, you can't understand this all straight away. it's just too much. But hopefully demystify them a little bit. Right. So I'm going to put the slides and video from the previous talks I've done. It's already up on my website at FP Toolkit. And just to plug, I have some online, if you're interested in this site, I have some online workshops coming up in September and November. And of course, I have my book that we just plugged. And I think I will contact me on Twitter if you have any questions, and I'll stop there. Thanks so much. And now I will answer any more questions that people have. And I'm happy to stay and answer questions for as long as you like. So any more questions from people? I don't see anything in the chat. Yes.
Yeah, I think yeah, we don't have more questions. Yeah, I will ask you a question. This is more, I would say, not exactly how these techniques work. If how you can, I would say, convince people to use them, or even you are working in a language, because probably you have a lot of experience in an environment that they want to use this kind of techniques, that the team is not ready, and if you use object-oriented language, it's even harder, right, to enforce these kind of ideas. And so I don't know if you can.
Yeah, it's hard to, I mean, people always say, you know, this is very cool, this is very interesting. It's really hard to change the way you think if you've been doing a lot of object-oriented programming. All I can say is that people who have tried it, a lot of people end up really liking it. So it's worth, I think it's one of the things where it's worth investing time to understand, because I think it will make you a better programmer. It's just another thing to understand. Just understanding object-oriented programming is good. Understanding functional programming is good. You know, understanding database programming is good. These are all good things to understand. So I think this is even though it's very strange to a lot of people, I do think it is worth investing the time to understand it. Now, the other question is, can you do this? You know, if you do this in C# or Java or JavaScript or something, those languages are not functional languages. They don't really enforce this way of programming. And so if you're learning, it's quite good to use a language where everything in the language kind of does it the same way. So if I would recommend, if you want to learn these ideas, learn using a functional programming language like F# or Haskell or ReasonML or Elm or something like that, because the way they do everything is this way. And so it's a lot easier to learn it when you're kind of, when you're forced to do everything this way, because you don't have a choice. So when you're learning now, once you understand the ideas, you can definitely apply these ideas in JavaScript and in C# and so on, because people do, and there are libraries that will help you do that. But I think when you're learning it, I think you should learn in a language which is specifically a functional programming language. I think it would be easier. Yeah, that's all I can say. But I do think it's worth trying out. A lot of people think it's overhyped, but I've definitely learned a lot from understanding this. It's helped me as a programmer, and so I recommend that other people take the time to understand it.
Yeah, completely agree. Yeah, that's a question that I've got a lot. It's talking actually about the same. It's that a lot of languages are getting a lot of functional features. C#
exactly.
included, like Kotlin, but they are lacking a lot of things to apply these techniques. I mean, they have a lot of stuff, but it's not enough, I will say. And you get frustrated if you, I don't know, what's your opinion in this?
Yes. I mean, for example, one of the things, a lot of functional programming, one of the key ideas is everything is immutable. So in F# and in Haskell and in Elm, everything is immutable, and it's just sort of built into the language. Now in C#, you have to do quite a lot of work to make things immutable. So it's not so you have to go to a lot of effort to use these techniques because the language doesn't like really support it. So yeah, again, I would say if you use a language where these things are sort of the default behavior, where immutability is the default and using functions is the default, and just all this stuff is just the standard way of doing it, it will be a lot easier to learn. And I think it would be hard to learn to do this if you're doing it in C# because you're surrounded by all the object-oriented way of doing things in C#, and I think it makes it very hard to switch back and forth all the time.
Yeah.
Yeah.
Okay. Yeah, we have lots of comments here about the talk that people like it a lot. And yeah, I think I don't know. From my side, from our side, it's a pleasure to have you here.
Yeah.
And it's been really, I've watched that talk a lot of times, and even 3 or 4 times it's hard anyway. So
it takes a lot of time.
Yeah.
So I say I don't expect people to understand all this. I mean, I threw a lot of stuff in this talk, but hopefully it's not so scary. I mean, the main thing I want to do is just show that these are tools for solving problems, and it's not just some academic theoretical thing that's not useful. But yeah, it does. There's no way you can understand everything in an hour, a couple of hours. It's not.